Alright, so in this video we're going to take a look at the June 2010 Unit 1 paper. So let's start off with some particle physics. So we've got a sodium nucleus decaying, forming a new nucleus, and it's doing it through beta plus emission. And one of the particles produced will be difficult to detect. So let's sketch what the general equation is. So beta plus emission is when a proton turns into a neutron plus a positron plus an electron neutrino. So it's the electron neutrino that's difficult to detect because it only interacts through the weak interaction, which has a range of about 10 to the minus 18, and is very small in magnitude. So it's going to be an electron neutrino. Now, most of these mark schemes will only ever want you to say neutrino, but I always believe in being as specific as you can be, so electron neutrino it is. Okay, write down the proton number and the nucleon number of the new nucleus. So during a beta plus decay, the nucleon number stays the same because we can see a proton turns into a neutron. So the proton number is going to be, the nucleon number is still going to be 22, but one proton is lost, so its proton number is going to be 10. Okay, name the baryon and each of the leptons formed a result of the decay. So the baryon formed as a neutron, and a lepton we have positron or an anti-electron, either with those would be fine. And then obviously we've got another lepton, the electron neutrino. So basically you can pick up all of these marks just by knowing what the generic beta plus decay equation is. So fairly straightforward. So we want to know the quark structure for a neutron is up, down, down, because that gives you a charge of plus 2/3 minus a third minus a third, and a proton is up, up, down, because that gives you 2/3 2/3 minus a third, giving you 1 overall. Alright, so let's move on to the next. Okay, so then last part of this question, drawing a Feynman diagram for beta plus decay, and you can see it's a quark Feynman diagram, and we're showing only the active quarks here. So a proton turns into a neutron, so an up quark turns into a down quark. Charge going in is +1, charge coming out of this one is 0, so there must be a positive charge going into the exchange particle, which is why it's W+. Then produced is a beta plus particle or a positron and your electron neutrino there. Again, some mark schemes will let you get away with just putting a V. Let's be precise, it's an electron type neutrino. Alright, so that concludes particle physics. Let's move on to the next question. Okay, so this question wants us to describe how the strong nuclear force between two nucleons varies with separation of the nucleons, quoting suitable values. So let's just do a quick sketch. So the diagram essentially looks like this. So above it's repulsive, down here it's attractive. So I'm just going to do this in bullet points. So separation is less than 0.5 femtometers. You should always write this out in full, by the way. I'm just short of space because the writing on this tablet takes up more space. The force is repulsive. And then so your separation is between 0.5 femtometers and 3. It's attractive. And then greater than 3 to 4 femtometers, there is no force whatsoever because you're outside the range of the strong interaction. And those will be the 3 points you need to make. So as I said, you would need to write this out in full. This wouldn't be okay to write like this. So separation is less than 0.5 femtometers. It's a repulsive force. So that's the area in this part here. Between 0.5 and 3, it's an attractive force. Then after 3 femtometers approximately, the force is 0. Those are your 3 key points. So we've got an unstable nucleus can decay by the emission of an alpha particle. State the nature of a alpha particle. So it's also known as a helium nucleus. So it's 2 protons, because helium's atomic number is 2, and it's also 2 neutrons, giving a nucleon number of 4. That's the key nature of it, and obviously it's going to have things like it's a +2 charge, that kind of thing, but that's what it's looking for. Complete the equation for alpha decay of uranium-238. So you'll meet uranium much more later in the end of the A2 course, but it's nice to have an introduction nice and early. So we're going to lose 4 nucleons and 2 protons. So we're going to have 2, 3, 4 on here, and we're going to use 2, so thorium has another atomic number of 90 there. Okay, so that completes this part, so let's move on to the next part of this question. So we've got 238 decays by emitting alpha particles and beta particles, eventually forming 206. Is a stable isotope of lead. What is meant by an isotope? So an isotope is atoms of the same element, so they're same proton number but different numbers of neutrons. So that's what we've got there, and those are the 2 key parts. That's where the 2 marks come from. Same number of protons for one, different numbers of neutrons for the second. Okay, so if there are 8 alpha decays to go from 238 to 206, how many beta minus decays? So 8 times by 4/2 means you're going to lose 32 nucleon number, and you're going to lose 16 on the proton number, so you're going to end up with something which has 206 and then 76 and then whatever that is. After all the alpha decays, we need to then go to 20682, so you want to keep the nucleon number the same but increase proton number, which is why beta minus decay is used. Beta minus increases proton number by 1, so we're going to need 6 beta decays there, so that's going to be 6. So marking this, or like working out how many marks, is fairly straightforward in this one. So the key thing is to recognize that this is what you end up with, so this is probably the first point, and then recognizing you need 6 plus 1s to get there would be the second part. So that's where you'll mark. This seems overly generous, frankly, for this question, but hey, who says exam boards aren't generous occasionally? So that completes this question on atomic structure. So let's move on to the next one. So we've got a clean metal surface in a vacuum, and it's being irradiated with ultraviolet radiation. So already in my head I'm thinking this is a photoelectric effect, and they're being irradiated with a certain frequency and electrons are being emitted, so it is the photoelectric effect. Explain why the kinetic energy of the emitted electrons has a maximum value. Okay, so generally speaking, this question is clearly asking about this equation, so let's do it in its rearranged. So the Ke max is the photon energy minus the work function. So the key points to address here are going to be the photons all have the same energy because they're being irradiated with a certain frequency. The material has a certain work function, so there's a certain max K. That's going to be the logic, so let's get that in. Okay, so that's the first statement. That's why we've got a maximum, because they all have the same photon energy, so they're going to get maximum kinetic energy of the photon energy minus the work function. However, some of them might be deeper in the material, which is why there might be less than that. So let's get that as well. So that's the second part. Some electrons are deeper in the material, and so will have a lower kinetic energy because it takes more work to remove them. So I always think of that, like if we look at the equation at the top, like an additional term in the equation there to explain why they're deeper in the material. They have smaller kinetic energy, and then that wouldn't be a Ke max, that's just a general kinetic energy equation. Okay, so that's that one. So if we explain with reference to the work function, why if the frequency of the radiation is below a certain value, electrons are not emitted. So let's first of all talk about what the work function is. So the work function is the minimum energy a photon needs to have to cause an electron to be emitted. Okay, so let's get that. All right, so we've got that. The work function, minimum energy for a photoelectron to be emitted. So now we need to link that to what's going on with the photons. So that means there's a minimum energy photon, and therefore there's a minimum frequency because we've got using E equals HF. So that's going to be the key equation. So that's what we've got there. So there's a minimum photon energy, there's a minimum frequency, because we can see those two are connected by a constant. So if the frequency is less than the threshold frequency, the photon energy is less than the work function. That's the relationship there. Okay, so state a unit for work function. Well, it's a unit of energy, so it's going to be in joules, or sometimes you'll see it quoted in electron volts or mega electron volts, that kind of thing. Those are your two units there. Okay, so light energy is incident on each square millimeter of the surface at a rate of 3 × 10 to the minus 10 joules per second. Frequency of light is 1.5 × 10 to the 15. Calculate the energy of an incident photon. So we're just going to be using E equals HF. So we know the frequency, we know Planck's constant, so this is fairly straightforward. And that would give us an answer of 9.9 times 10 to the minus 19 joules there. Fairly straightforward. We've got the frequency. Okay, so let's move on to the next part. So we want to know the number of photons that are incident per second on each square millimeter. So we know the total energy incident, and we know how much energy each photon has. So we need to then use that to work out how many photons there are per second. So the energy total per second was, we got that earlier, that was 3.0 times 10 to the minus 10, and the energy of one photon was 9.9 times 10 to the minus 19. So essentially what we need to do is to get photons per second, we need to do a little bit of jiggling around. We need to take our value of energy, this is how much total energy there is per second. We need to divide that by the energy of each photon, so 9.9 blah, 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 times 10 minus 19. And if we do that, we can get a total number of photons per second of 3.0 times 10 to the 8. Nothing to do with the fact it's the same number as the speed of light, it just happens to be in this case, and that's in photons per second. And I always like to make sure we put a unit there. There, photons per second. Okay, so then in the wave model of light, electrons on the surface energy absorb energy from a small area of the surface. Light striking delivers energy at a rate of 3 times 10 to the minus 22 joules per second. The minimum energy required to liberate an electron is 6.8 times 10 to the minus 19. Calculate the minimum time. So to get a unit of seconds, we're going to do the unit of joules divided by joules per second, because that's, you can see the joules are going to cancel out and you're going to get S on the top line because it's 1 over S on the bottom line. So what is that? So we need 6.8 times 10 to the minus 19 divided by 3 times 10 to the minus 22. And we can see that if we put that in the old calculator, we get 2.3 times 10 to the 3 seconds. there. So a long period of time, but a time nonetheless. Practice the time delay calculated in part C does not occur. Explain how this experimental evidence was used to develop the particle model for the behavior of light. Okay, so particle model of light predicts that all emissions will be instantaneous. Wave model says it can just take a period of time. So essentially, the fact that there is no time delay in emissions tells you that it's the particle model of light that is explaining what's going on. So that's the general theory. Let's now try and put that into words for this question. So what this allowed us to do was conclude that light travels as photons. This was the conclusion because the prediction of wave theory did not occur, but the prediction of particle theory or photon model light did occur. And what that means energy is transferred in discrete quanta. So that's what we got there. Light travels as photons, which means energy is transferred in discrete packets. That's what the experiment evidence told us. Or conversely, you could think about it because from this experiment, the wave model was rejected because one of the predictions of the wave model has been shown not to be correct. That's most of the time what you'll find when you use science experiments, that your hypothesis is wrong. But in this case, it's the particle model turned out to be correct. All right, so that concludes this question. Let's go on to the next one. All right, so this one says electrons exhibit wave-like properties. So the previous question, we looked at the particle model of light. Now we look at the wave model of particles. So what phenomenon can be used to demonstrate the wave properties of electrons? We don't need any details. So essentially, this is just looking for a very simple answer, and that's electron diffraction. So diffraction is a wave property only. It's not a property predicted by particle theory. So if you can make electrons diffract, that would mean they're acting like waves. So that's the evidence. Okay, so we want the wavelength of a particle with this speed, and it's an electron, so we can look up its mass in the formula sheet. So this is the equation we want. So it's going to be 6.63 times 10 to the minus 34, divided by, when we look it up, 9.11 times 10 to the minus 31, times by 4.50 times 10 to the 5. We put all that together and we will get an answer. Let's just put it in the calculator. And we get an answer of 1.62 times 10 to the minus 9 meters there. So about 10 times the size of a regular atom, that kind of thing, with a regular atom being about 10 to the minus 10. So the last part, a muon has mass equal to 207 times that of an electron. Calculate the speed of muons with the same wavelength. So if they have the same wavelength, what we can do is a nice little trick. So wavelength of 1 is equal to wavelength of 2. That means h over m1 v1 is equal to h over m1 v2. We know Planck's constant is the same, so what we can do is we can get v2 in term as m1 over that's going to be m2 over m1 v1. We know that m2 is, which is going to be 207 over v1. So let's do that. So its velocity is 4.5 times 10 to the 5. 7 divided by answer gives you so I just realised that's 1 over v2 is that. So we've got that. So flip that my answer over, and we end up with v2 is 2.2 times 10 to the 3 meters per second. So I just realized when I was going through this, I didn't calculate V2, I actually calculated 1 over V2 if you rearrange this equation correctly. So then I calculated this, flipped it, and you end up with this number right here. Okay, so that concludes this question. Let's move on to some electricity. Okay, so the student wishes to investigate how resistance of a thermistor changes with temperature. So first of all, we're going to need to draw a diagram of how that works. So the way we're going to control temperature is using a water bath. So you can see that there, and you can see the thermistor has been plonked into that hot water bath. A voltmeter is kept in parallel across the thermistor. An ammeter is used to determine current, and we've got our power source to provide some current in the first place. I've labelled the water bath because it's not a standard component. This thermistor is there. So that's the general setup we would use. The next part is inevitably going to be describing how we would use it, and hell's a breeze, it is. So in terms of how we would go about getting values of temperature and resistance, we're going to want to set up the circuit we've got above, so we can get values of resistance by measuring potential difference in current and using Ohm's law to determine resistance. So that's what you can see here, and we're going to set them up as we've shown. So for the first measurement, we're going to heat to 80 degrees. We're going to allow the system to settle so everything reaches the same temperature, or the fancy word for that is thermal equilibrium, and we might want to speed that up by stirring it just to ensure everything is the same temperature. And we can then check what the temperature is using a digital thermometer to improve your precision of your measurement there. And you're going to want to make sure you take that measurement as close to the thermistor as you can. So you've got the temperature right, put your thermistor in and determine the resistance using the strategy we've outlined. Then repeat that process for different temperatures, so like 70 to 20 for instance, and get resistances for every temperature. You're going to want to repeat the whole process because that will give you average resistances at each temperature, and you'd have a resistance versus temperature graph to look at the relationship between the two. So let's just check the criteria that you were asked for. So you wanted to obtain accurate and reliable measurements. So the strategies to make it accurate and reliable: you've got your digital thermometer, you've got allowing it to reach thermal equilibrium, you've got the fact you've taken repeat readings to determine average resistance, and you've got a good range of temperatures. Those things would all be what you need there. Okay, so that finishes that practical based question. Let's do some theory stuff. Alright, so we've got a battery of EMF 6 volts and no internal resistance. We've got a series thermistor and resistor. And the temperature is 50 degrees. The resistance of the thermistor is 1.2 kilo ohms. The voltmeter across R reads 1.6. We want to know the potential difference across the thermistor. So it's going to be using Kirchhoff's series voltage law, because the sum of the PDs equals the sum of the EMFs. So that's going to give you 4.4 volts as a potential difference there, because 4.4 plus 1.6 is 6. We want to know the current in the circuit. So we know the potential difference across the resistance, and we know the resistance. So current through the thermistor is going to be the potential difference across the thermistor divided by the resistor. So the PD is 4.4. Its resistance is 1200 because it's in kilo ohms. When we calculate that, we get a current of 3.7 times 10 to the minus 3 amps there. That's your current in your circuit. And if we look at the diagram, the current through the thermistor will be the same as the current through the resistor will be the same as the current through the battery, because it's all a series circuit and we're assuming the voltmeter has infinite resistance. Okay, so that finishes that part. So the first stage is asking us to work out now what resistance is. So there are a few ways of doing this. I'm going to show you the method that I've used. You could have also used Ohm's law to do this, by the way, which would have been more straightforward, but this is more interesting. So I'm looking at a potential divider equation, and I've put it in to work out the potential difference across the thermistor, because that way only one unknown features in here. So let's do that, and we're going to rearrange that to make the total resistance the subject. So that's what I've done here. So EMF, potential difference across the thermistor and the resistance of the thermistor, and when we do that, it comes out as 1636 is the total resistance. The total resistance is also the sum of the resistors, so subtracting 1200 gives us a resistance of 436 odd, so 4.3 times 10 to the 2 sig figs there. Okay, so then it's how would the reading we've got change for part, how would the value we change for part B change if there's the internal resistance is not negligible? So that would essentially mean there's another value in this equation here. You'd also have to add on the internal resistance, so that would have the effect of giving you a smaller resistance. So, but we're also entering the voltmeter reading on it, so what's going to happen is the total resistance is going to increase if we have internal resistance, which means the current is going to decrease. We've got the same EMF, but now increased resistance, the current decreases. So if we look at Ohm's law, the resistance of the component itself, the resistor, stayed the same, the current has decreased, so that's going to have the effect of decreasing the voltmeter reading. Okay, so the way people often get jumbled up with this is they've gone, well, R's increased and current's decreased, so V stays the same. The key to recognize using Ohm's law is the resistance of the actual resistor itself has stayed the same throughout. So if current decreases, the voltmeter reading decreases. Okay, so that finishes that question there. Let's move on to the next one. Okay, so a semiconducting diode is an example of a non-ohmic component. What is meant by a non-ohmic component? So essentially the current through a device is not directly proportional to the potential difference across it. Okay, so that's your non-ohmic component. Another type is a filament bulb. Sketch a current versus potential difference graph. So we've essentially got it sloped here, it becomes roughly straight lined, and then this. So it should be roughly it should be symmetrical, sort of. So it kind of the same shape on both ways, and then decreasing gradient towards the end. It's a little bit wonky, but never mind. So with reference to the IV characteristic, how the resistance of the lamp changes as the PD across its terminals changes. So what happens is the resistance increases, so I'm just going to do that for shorthand, and the reason we know that, so I just wanted to state is so resistance increases, that's all we need to do, we don't need to explain or describe or anything. A filament lamp has a power rating of 36 watts when there's a potential difference across the terminals of 12 volts. Calculate the resistance of it. So we're going to be using this equation right here. To get resistance, we need V squared over P. So 12 squared over 36, which is 144 over 36, which is 4 ohms. There. So that's that one. Let's move on to the next. All right, so let's look at the final question. So we've got a 10 ohm battery connected to a 6 volt power supply, and the EMF, so that's the EMF is 6 volts. This looks very much like the internal resistance experiment. So I'm going to define the EMF. EMF is the work done by a power source on each charge passing through. Or as you often see it, work done per unit charge by the power source. So that's EMF. When the switch is open, the voltmeter reads 6 volts, and when it's closed, it reads 5.8. So explain why the readings are different. So the voltmeter is measuring the terminal voltage, which is calculated using this equation. So when the switch is open, which I'll call scenario 1, switch is open, current equals 0. So that means that the terminal voltage and EMF are the same. So in scenario 2, when you close the circuit, the current has increased. So now the terminal voltage is the EMF minus a part. So as current is increased, that's going to have the effect of decreasing the terminal voltage there. And the reason we can explain that is essentially there's some energy lost across the internal resistance. So the reason it's changed is there is now potential difference across internal resistance. And why is that now there? Because the current flows. Alright, so let's finish that one and move on. So the next part is asking us to calculate the internal resistance of the battery. So we're going to be using this equation here. You realize I made a small error. I really should be using a little r, otherwise it gets confusing. So the first stage is to work out what the current is. So we know when the switch is closed, there's a potential difference of 5.8 volts across a 10 ohm resistor. So we can work out what the current is in your circuit. Then by rearranging the top equation, we can determine the internal resistance of 0.34. And it's a small value, which is what you'd expect. Most internal resistances are quite small for general components. So then we're going to look at how we can use that, state and explain why it's important for car batteries to have very low internal resistance. So essentially, batteries need to supply high current or high power because they need to start a car. So let's write that. So that's what we've got there. So batteries need to supply high current to deliver high power because we need to start an engine. And you can see from this equation, this R represents the external resistance, so we don't need to worry about that. So the higher current it can deliver, the higher power it will deliver. So essentially, internal resistance has the effect of increasing total resistance, which, because EMF is the same, means total current decreases. So then we've got the second part there, as I just explained. Internal resistance increases total resistance, because it's in the circuit, which decreases the total current, because EMF stays the same, and decreasing current decreases the power available. So that's why you want to minimize internal resistance. Okay, so that concludes this video from the June 2010 Unit 1. I hope you found that useful. If you spotted any errors in my working or anything that wasn't clear, please do comment and let me know. If you can't read my handwriting, sorry about that, but there's not much I can do about that. That's why I talk through it as I go through. Thanks very much for watching, and I hope to see you again soon on one of my other videos.